All right, now we get to the not as fun stuff, but fine. We'll learn about some other things here too. Let's go back to our equation we were studying, ut equals c ux, one-way wave equation. And what we talked about is all these different schemes sort of to discretize this in space and time. Okay? Oh, I saved a seat for you, Charles, with your jacket even. You're welcome. I don't know. You're going back. I thought you'd be front row for sure. I don't know. Okay. Oh, is that a broken seat? Okay. All right. I didn't realize that. All right. So anyway, I give you about 5 or 6 different schemes that you could step forward into the future with for that equation right there. And what we talked about is there's 2 things you always have to consider in a scheme: stability and accuracy. Answering the question about accuracy is pretty easy, right? Because you're going to pick a discretization. You say, is it second order accurate, fourth order accurate? So you already know the accuracy properties. But the stability properties then become the important issue to address. So one of the ways we did this was through forward Euler. And let me just write down what our scheme became. Our scheme became the following. And if you want to look back at last notes, you can see this, but let me just write it down. You just have to trust that, in fact, I wrote it down correctly, which I did. There it is. A point in the future. Remember, n, let's remember what these n and m's are. U at some x of n t of m is equal to u n m. So you go, remember, we're going to discretize space and time. So when you're to nth location, that's your x of n, and at the nth time, okay? So this is our shorthand notation for this, okay? We are being green in this class by writing it with compact notation, and we save so many pins. All right, see, yeah, all green. It's like Seattle or something. All right. So we have this scheme where it says the point in the future is what it is now plus something, and this something is the CFL condition, lambda over 2, and then using my 2 neighbor points. And the 2 neighbor points tell me about derivatives. Okay? Pretty simple scheme. You have everything you need. You give an initial condition, you can march forward into the future. Now, I made a comment that, in fact, this scheme was stable no matter how you pick your CFL. And then so the question is, well, how did I know that? Okay? So what we're going to talk about today is what are called a von Neumann analysis. Okay? I think it's 2 n's. Yeah. Unstable. Sorry. Unstable. Regardless. Sorry. All right. On the von Neumann analysis. Now, this is named after John von Neumann. He was one of the guys that worked. He's a pretty famous mathematician. Some credit him with the invention of, like, the computer. But, you know, he was working back in the mathematician working back in the day. He was also with Manhattan Project, was doing some of the first initial computations. And what they were studying were basically blast waves. What they wanted to do, set up a bunch of TNT around a uranium core and then blow that up, make a big blast wave that would compress this uranium, and then you know what happens. Boom! Okay, all right. So there we go. That's what he was studying. So back then you wanted to sort of do these calculations. First computers were kind of thinking about these algorithms and doing this. So he was very early on and saying, hey, okay, I got to come up with a scheme. And this is the kind of schemes they were coming up with. How do we think about that? And by the way, you know, before the computer came on, here's what a computer was. You guys. Look at this iteration scheme. I grab some points. I do a computation, send it up to the future. What you guys are around here, arranged in desks or rows, it's there's my spatial discretization. I'm going to march forward in time. You calculate your points. When you get them together, you send them to the person behind you, right? You 3 send your results to the person behind you. That person's now t of n plus 1. You all calculate t of n plus 2. Okay? This is the computer, the early computer. You think that's exactly what they did. Lines and lines and lines of people, mostly women, just computing. And what they were computing, blast waves. And then the computer came along, and then that's it. Okay? Now you have my magic iPhones to do all this. A little bit of history for you there. So what does von Neumann propose to do? What von Neumann proposes to do is said, look, I really want to know about the stability of the scheme, and it was well known in PDE theory that one of the ways to solve PDE theory is to get solutions out is to do separation of variables, separate time and space. And what he says is, let's do the following then. Let's go ahead and say that U of nm has two components. Here, where h is my discretization. I don't want to write delta x every time, so I'm going to write h. So he says, look, I'm going to do the following. Write it down as some constant g to the nth power times e to the I c of n h. Okay? So what is this? This is my spatial stuff. This here is my time stuff. N, remember, is space. M is time. What are these? Cosines and sines. So really what he's saying is, let's expand everything out in Fourier modes. And I can just ask the following question. What does it mean to be stable? Well, if I'm going to iterate forward m and take m to be going to infinity, then what I really want to know is the following two things. In the limit, as m goes to infinity, does this thing go to infinity? Because if it does, my scheme's going to blow up. Okay? So if you have that, then this would be an unstable scheme. Okay?
I'm sorry, is it true that U sub n equals G to M E?
You're making this up. You are going to shove this in and see what happens to it. That's all you care about. It's not anything equal. You just say, I'm going to assume this solution form, throw it into, sorry, I see a nice curve, into this scheme that I came up with, and ask what happens to this thing as I iterate. So it's one specific type of solution. Fourier modes. Okay? So it's limited, but if it blows up, you know you're going to have problems. Because Fourier says, I can take any generic function, and I can represent it as sines and cosines. So to some extent, you could always say, I can always take any generic function and put it in here to iterate. And it is a bunch of sines and cosines. And if I know what happens to those, then I'll know what happens to everything. Okay? So plug it in there. And by the way, so that's the one thing that happens there. And the other thing you want to know is, well, a stable scheme would be that if you look in the limit as m goes to infinity, that, in other words, you just want this thing to be less than infinity. That's not asking so much. So really, all you care about is this g, the absolute value of this g. What these really relate to is, if g is bigger than 1, problems, right? Take a number bigger than 1, you keep raising it to an infinity power, this thing blows up. Okay? Whereas g is less than or equal to 1, then you're okay. That's my take on that. Okay? Everybody good with that? That's what it means to have a stable scheme or unstable scheme. So let's go apply this back to this forward Euler equation.